Buenas tardes. June 29th, 2019. Our subject today is Bhaskara. But first, to introduce polynomials of any degree. It's a bazooka for killing mosquitoes. We go through Lambert functions, hypergeometric functions, theta functions, Glasser's derivations. An algebraic number is a kind of combination of radicals in such functions. We have intention to pass through Galois theorem and solve polynomial equals to 0 for complex variable and for any natural n. We intend to solve polynomial of t equals to 0 for complex coefficients or even in the commutator of linear transformations of squared matrices t from Rn to Rn. We intend to translate smoothly one polynomial to another by Girard's equations or Newton's identities, by ordinary differential equations. Its intention to pass through exponentials and logarithms of matrices, but commutative matrices. Non-commutative is beyond of this subject. It's our intention to solve exponential of complex equals to complex, exponential of matrix equals to matrix. It's our ambition to solve exactly exponential of x equals to polynomial of second degree and also degrees greater than 2. And now it's our last intention to classify polynomials by real or complex roots and by multiplicity and in degree, and for each class we intend to present an example. So, sketch. First comes Bhaskara with failure. Then we present what we got with ordinary differential equations. Then we try to reduce exponential to Bhaskara. Then exponential of z equals to z is almost Bhaskara. Then solve Bhaskara by Lambert. Now we go to quintics. Now we go to straight line. Degree 1, companion matrix 1 and 2. Degree 3. Degree 4. Degree 5. Hungerford fastly shows us why the quintic is unsolvable by radicals. Our result of any degrees. The exponential of RIT is equal to 1 f1 of t plus ri f2 of t plus ri squared f3 of t until rin and factorial fn plus 1 of t. We have polynomial of nth degree of x with real coefficients equals to 0, Pn of x equals to 0, and we have exponential of xt plus the polynomial of n minus 1 degree of x with coefficients I of t equals to 0, and we're going to show it for n equals to 2. Then we have example, the classification for distinct real roots, real coefficients, repeated real roots, real coefficients, complex conjugate roots, real coefficients, and if the roots are not conjugated, the coefficients are complex. It's not our subject. Then The file has degrees 3 and 4 and 5. We classify degree 2 with 3 classes, degree 3 4 classes, degree 4 9 classes, degree 5 12 classes. We show that an extended polynomial key of x is generated by the following context-free grammar. From an empty string lambda, we get almost a polynomial from e equals to 0 to n summoned of si. Each si is ti or ai multiplied by bi power to x or f of si, where f is hyperbolic cosine, hyperbolic sine, ordinary cosine, ordinary sine. Ti can be replaced by ai x power to I or minus I. X can be replaced by another sum from I equals to 0 to n to summoned si. So many times you can go to cosine of the sine of the square of the cosine of the sine of the square of x. Given the coefficients of an input polynomial and without the roots, we know the coefficients of x minus key of R1, x minus key of R2, x minus q of Rn. Okay? A family of coefficients. All we need is that q is the same and the roots are any. This shows that every equation is almost the same equation because there exists a q that transforms R1 R2 to R1 line to R2 line, right? When we go to infinity, we conjecture that key of x must be almost everywhere analytical function. So a Taylor series analytical can be derived from this context-free grammar when n is equal to infinity. So the sketch of hypergeometrical method I found for the quintic, but I'm not sure that is possible to zero everybody 1 2 that n minus 2 for 6 7 8 9 and 10. But here is the method. We get any polynomial and another polynomial of 1 degree less plus y equals to 0, and we have a determinant of a matrix n by n in function of the s's of p, the sigmas of q and y, and this determinant is a polynomial of y degree n, and each coefficient is a polynomial of degree n minus 1, n minus 2, 2, a and b. Okay, so we have to solve equations of degree 1 equals to 0, degree 2 equals to 0, degree n minus 2 equals to 0. We have to evaluate the inverted p of 0. We have to evaluate a, evaluate b, where a and b are the last polynomials. Then we have the Briggs normal form, y power to n plus ay plus b equals to 0. and exchanging y this way and exchanging t this way, we go to z power 2n minus z plus t equals to 0. It is an open question what happens when we are at the commutator matrices, because when z is complex, we have n plus 1 fn, hypergeometric function of complex numbers, and I still don't know hypergeometrical functions of matrices, and what worse if they do not commute. After evaluate z, you evaluate y. Y is z multiplied by minus a powered to 1 over n minus 1. Solve recursively q of x, y equals to 0. Remembering, q is 1 less than n. Store the n minus 1 roots into R. Choose x1. One of these Ri is a function of sigmas and y. Verifying each Ri if it satisfies Pn of Ri equals to 0. Yes, no, cancel? One of them is a root. Sure. Divide pi n of x by this x minus this root. You'll have an exact polynomial in sigma lines, degree n minus 1 equals to 0. We have y line equals to 0 by the same prototype. Here we have q xy, here we have q line xy line, but our y line is 0. Solve recursively another q line x0 equals to 0, and these n minus 1 x's, which are functions of sigma line and 0, are what we want. Okay, so let's begin again. As we have seen in our last videos, when we try to solve an ordinary differential equation of degree 2, a y2 lines plus b y line plus c y of t equals to 0, we have an exponential of a matrix times t times c, which is also c1 f1 plus c2 f2, but they are not separated by exponential of r1t and exponential of r2t. So we cannot solve the polynomial this way. What is true Bhaskara? When we exponentiate this matrix, we get f1, f2, f1 line, f2 lines, where this is the exponential of tm. Identity plus tm plus t2 over 2 squared plus m2 plus t3 over 6 m3, etc. Okay, this is Taylor series of the exponential of tm. Let mijn be the ij cell of the result of mn. Here we have f1, here we have f1 line, here we have f2, here we have f2 line. 1 0 0 1 is the identity. 0 m2 1 1 m2 2 is m. M is 0, 1 minus ps. So here appears line 2, column 1, minus p. Then we have discovered that the exponential of xt is this expression. This is Taylor series. And the matrix we want is the exponential of Tm times the transpose of T. 1R1, 1R2. And we can't solve it without knowing R1 and R2. So we discovered xn equals to m11n plus x m12n has R1 and R2 as roots plus other roots, and the exponential has the same real roots plus 1 infinity of complex roots by the branches of logarithms. But the two roots R1 and R2 are particular cases. And for instance, x3, x4, and x5. And here is the conclusion. The exponential of Tm is the inverse of T, 1 over the determinant multiplied by the exponential matrix multiplied by R2 minus 1 minus R1, 1. So without separating R1 from R2, we cannot solve the system. This is the solved exercise. By means of S and P, we have to substitute. R1 is S plus square root of delta over 2, and R2 is S minus square root of delta over 2. Then we have the solution, function of S and P. Now we go to companion matrix 2. We discovered that for this companion 0, 1 minus ps, the equation holds. M2 minus scalar Sm plus scalar P times identity equals to 0. The exponential of the same mt is also f1 of t plus f2 of t times the matrix M. And with this block of Jordan, it seems 0 plus 2 key p I. It's complex. A minus b, b, a. A equals to 0. The exponential of m is the identity if and only if m is the logarithm. The logarithm is a set of pj pn powered to minus 1 inverse of p, where j of key is that Jordan form and determinant of p is not 0. For any subset of z, sum of every j's and every p's, it's a countable sum. So next step, we want the logarithm of t. Exponential of m equals to t, so m is the logarithm of t plus l. L is the logarithm of the identity. So we have A matrix T powered to a matrix M, what is it? The exponential of M ln of T plus L. Exponential of ln of T plus L M. That's a commutative problem. T powered to M f1 of T matrix plus fm or mf2. Who are logarithmizable matrices? They are similar to A00B, where A and B are greater than 0. Complex numbers, not the zero complex number. And AA0A, where A is greater than 0. Theorem. The identity commutes. Identity M is equal to M identity. Therefore, the logarithm also commutes. M logarithm is similar to logarithm M. Every Jordan matrix has a similar companion matrix. Reciprocally, every companion matrix is similar to a Jordan matrix. The identity is a Jordan matrix, of course, because A equals to 1, B equals to 0, complex form. After the equation 81, we discovered this. What is 81? The logarithm of the companion matrix. So, where were we? T2 minus ST plus P equals to 0. Matrices T, S, and P. We want to use Bhaskara, so we want that TS equals to ST. Then we can complete the square. 1 over 4 of S2 minus P is the square of a matrix. It's VD2 V inverted. Then the solution T is 1/2 of S plus VDV inverted, where D is the square root of a square rootable matrix. Square root of A2 0 0 B2, the diagonal greater than 0 or 0. Square root of greater than 0 in diagonal the same number, and 2 times it's the square root. And any complex number, and A2 times identity, because A and B are different, and here A is equal to B. When the identity appears, V and V powered to -1 cancel. When do we go back to complex numbers? Plus or minus the diagonal, the identity. Now we're going to the exponential, from exponential to Bhaskara. We have the equation A plus bx equals to c powered to x, and we want x2 minus x sx plus p equals to 0. Then we go back to those equations, and f1 of logarithm of c is a, f2 is b, and who is the derivative? We do the calculations and appears minus pb, and f2 line of the logarithm of c is a plus sb. Now we want s. To appear s, we sum one exponential to another exponential, and appears 2 here and s here. Who is s? Function of a and b. and multiplying x1 by x2, exponential of r1t minus f1 over f2 multiplied by exponential of r2t minus f1 over f2, we have p, x1, x2, r1, r2, c powered to s, etc. And we know who is p, a function of s, a, and b, and c. When delta is 0, etc. And we cannot invert the logarithm of a and b because it depends on the second line p and s. How we solve this equation in p and s? Ta-da! Next step, exponential of z equals to z. Brouwer fixed point theorem. We need fixed points for the exponential, and they are complexes. I found 5 with 10 powered to minus 14 error. That's my epsilon. And we still don't have a formula for w of minus 1 is p plus key I, and their conjugates are solutions. Here is the reasoning. Exponential of z equals to z multiplied by exponential of 2kpi is cosine of 2kp is 1. Z is logarithm of z. Okay, logarithm both sides. Z is r exponential of it. Logarithm of this form is logarithm of r plus at plus 2kpi. These are the branches of the logarithm. So we have two equations, r cos t equals to a natural logarithm of r sin t equals to t plus 2kp, and z will be the solution of this system. For each n, for each key, for minus 1, we have w of n key minus 1 with opposite sign, and the conjugate is also a solution. And the solutions of the polynomial are extracted from the solutions of the exponential modulo m. What is modulo m? All we know until now is the real roots are the same. Who wants real roots? I want complex roots. So here is an exercise, the theorem. I solved exponential of m equals to m. If and only if m is p big P small p v minus q u big P inverted small p plus q I is solution of this equation. Logarithm of the same thing plus a minus bi is a constant. Logarithm of u plus vi plus constant is u plus vi, and the matrix A, B, C, D with the same P inverted and P must be the identity, a kind of L. And we have a system of two equations, exponential of xu, exponential of xv, ax plus b, cx plus d, and we want to solve it, reduce it to Bhaskara. We set alpha exponential of u and beta exponential of v equals to alpha 2. We choose logarithm of alpha equals to u. We choose logarithm of alpha times 2 for v. From all those t's, we have two particular t's. Then we isolate x. Multiply the first by c. Multiply the second by a. Subtract, cancels acx, cax, and remains bc minus ad. Now, this guy is alpha power 2x. This guy is alpha power 2x's. And alpha power 2x is our y. Now we have Bhaskara. A y2 minus c y plus bc minus ad equals to 0. And everybody knows that y is a quadratic formula and x is only the logarithm basis alpha of y. So we translated R1 and R2 to the coefficients of alpha powered to R1 and alpha powered to F2. Okay? Example. y2 minus 4 cosine of ln of 2y plus 4 equals to 0 if and only if y is 2 powered to 1 plus or minus I. So Bhaskara's family is xn equals to ax plus b, exponential of xt equals to ax plus b, and y squared minus s of t y plus p of t equals to 0, where y is the exponential of xt. Next step, we solve it by Lambert. At Wikipedia, we know that when delta is greater than 0, we have two solutions, n equals to 0, n equals to minus 1, x1 and x2, 1 over at minus a w Lambert function applied to minus t over a exponential of bt over a. All of this minus bt. All of this over at. This is the solution x. Bhaskara can be solved by other means, therefore every polynomial equation is solvable by generalized Glosser's derivations. That's what we are going to prove. Let me see if remains straight line. Okay. Descending to n equals to 1. Again. N equals to 1. Our method says that x equals to r1. We go to the exponential of xt, exponential of r1t, function 1 of t for all t. A is b powered to x, x is r1, x minus the sum is equal to 0. So the sum is r1, and r1 is the logarithm of a over the logarithm of b. K is equal to 0, the branch of the logarithm. So the exponential of t is b, and t is the logarithm of b. The f of the logarithm of b is a, and everything is equivalent. And the straight lines family is x powered to n equals to a, exponential of xt equals to a, and exponential of xt minus a function of t equals to 0. We did that for n equals to 2, for n equals to 1, and next video we're gonna do it for n equals to 3. Companion matrix 1. Whenever a of t is the exponential of tm, whenever b of t is the exponential of t times identity, whenever a is the b powered to the matrix M, what we can say? We can say that the logarithm of A is m logarithm of b, or logarithm of b times m. And m is 1 times the other, or the other times the 1, modulo L. What I'm trying to say is that for all t in R, there exists a single m solution of the system in Rn. We want the logarithms of A on the basis B at one parameter. Okay? So that's what we did over above. ln of A over ln of B when A and B are complex numbers. In the ln of A and ln of B when A and B are matrices. Now let's see cubic, quartic, quintic, hundredfold, variation of parameters. I'm going to explain. We have a set of roots R1 and R2. Cartesian product with R when T is in R equals to 0. It's a family of the same equations. And for each term A of the Taylor series exponential of RT, sum of R power to A over A factorial times T power to A, psi A of XA is a polynomial x power to A plus a polynomial of degree n minus 1. And the solutions are the inverse set point 0, the R1 and the R2, Cartesian product n, where A is any natural number. Here are the examples. x2 plus 5x plus 6 equals to 0. When A is the exponential of minus 2 minus exponential of minus 3. When B is 3 exponential of minus 2 minus 2 exponential of minus 3. We have the same solutions. Hello. We know the solutions are minus 2 and minus 3. Here is the graph, minus 2, minus 3. Any other is different than 0. Number line, minus 2. Integer solutions, minus 3, minus 2. So we diagonalize minus 2, minus 3. Here is the companion matrix. Here are the eigenvalue vectors. Here is the inverse VDV inversed. Here is the example for x3, x4, and x5. This quintic has two complex roots and has minus 2 and minus 3 as roots, and we went through x6 and x7 too. Now repeated real roots. When r is minus 2, we have the characteristic equation y 2 lines plus 4y line plus 4y equals to 0. So f2 is t exponential of minus 2t because of reduction of order. That's what we learn in ODEs of repeated real roots. This is Bhaskara when x minus r powered to 2 is equals to 0. x2 minus 2r plus r2 equals to 0. r equals 2 minus 2. The equation is solved because the exponential is isolated, the RT is isolated, and the R is a function of t isolated. That's not relevant to solve a particular case, but that's interesting. So the Jordan normal form is minus 2, 1, 0, minus 2. The eigenvectors are 1 minus 2 and 0, 1. Here is V inverted. We calculate the cubic, the quartile, and the quintic. Now, complex conjugate roots. When delta is less than 0, we have the roots a plus bi, a minus bi. For instance, 120 degrees unitary times I exponential. Okay? Minus a half plus square root of 3 over 2i is the exponential of I times 120 degrees. So we have f1 of t function of abt, f2 of t function of abt. The exponential of x is cx plus d. We can approximate c and d, and we can diagonalize a minus b, b, a, eigenvectors a, b, 1, 0, and 0, 1, 1 over b minus a over b. Then we have x3 equals to 1, x4 equals to x, x5 plus x plus 1 equals to 0. 4 complex. The complex are all different and conjugate, and one single real. Who is the real? No, we know a plus r minus b are so two of these solutions. We can solve it by Glasser. Glasser is a method for solving Brink's normal form. But we're not going to reduce hypergeometric to second degree. That's possible. That's an exercise. And now we have third degree. And now we have fourth degree. Now we have fifth degree. And we conclude that for all degree, it's always the same thing. This work began at May 17, and out of charity, there is no salvation at all.